And now we are going to start with all the technical talks. As you know, we have a packed program, so we will skip the questions. You will have the long breaks to interact and network with all of our sponsors and the rest of the community, so take advantage of that, please. So now I would like to invite to the stage to Travis Lanier and Greg Favor, please. They are members and they work for Ventana Microsystems, and they have a lot of experience in the semiconductor industry.
So our CEO, Balaji, was supposed to be giving this keynote today, but he couldn't make it. So I'm excited to be giving it on his behalf. With me, I have Greg Favor. Our careers have intersected over the past 30 years ago, all the way back to when I was at AMD. Some of you may remember something from the 90s called K6, so Greg was the key architect on that. The second time I crossed paths with him and Balaji was when I was managing something called Cortex-A15 at ARM. We were attempting to get into data center. And so Balaji and Greg came along and decided to do the first 64-bit ARM processor. So I'm super excited to be working with him at Ventana doing high-performance RISC-V and taking that to the data center. So with that, let's get into Balaji's keynote. So last year we were on this stage, and it's been 1 year since we shared our vision, and it's been a fantastic year. Ventana had a breakout year both for ourselves and for RISC-V. We've seen a lot of traction with customers committing basically hundreds of millions of dollars towards the development of RISC-V in the data center. We've seen excellent traction. And so they're committing, this is not just hype, so it's real engagement, real revenue, and accelerating. So why is this happening? Because we're making it frictionless. We're removing the barriers to RISC-V adoption in the data center, and customers are responding. You may have seen this slide before. We said frictionless, and this is what it looks like. One of the biggest reasons Ventana has seen such strong traction is our complete platform. We're not just delivering IP. We're delivering real systems built on a scalable chiplet architecture ready for data center deployment. We make RISC-V adoption frictionless, from silicon to software, from system IP to full reference platforms. Everything is in place. Customers aren't starting from scratch. They're starting from a running start. That level of completeness is why adoption is accelerating. Customers are moving fast and investing big to bring RISC-V into their next generation products. Last year, we also outlined this. We showed how RISC-V can unify AI acceleration. On the right, you see a variety of people trying to attack the AI space. And all of them have a proprietary ISA and have to build their own software stack, which leads to fragmented software ecosystems. Additionally, these are loosely coupled to the main compute inside the system, which introduces inefficiency as data moves back and forth. RISC-V solves this by enabling ecosystem scale. You have a shared ISA across the CPU and accelerators, and it can scale to various levels of AI performance that's needed. This enables for a common software stack. This is the difference between a collection of chips and a unified compute solution for AI. This is what we showed you last year. After laying out the case for unified RISC-V as a foundation for AI, we took it a step further. We said RISC-V could go toe-to-toe with one of the best platforms for AI in the industry, the Grace Blackwell platform. On the left, you can see a system put together with an ARM Grace CPU and then the AI accelerator attached to that. On the right, we said, hey, we can take the same building blocks and do that in RISC-V. In this case, we're using our Veyron V2 to replace the Grace portion of it. And then you could use our Veyron E2 processor, a soft chiplet IP, and use that to create the AI acceleration. So this is no longer a concept. This is actually Ventana's platform and blueprint for creating AI acceleration platforms. And on the next slide, we'll talk about how our partners are putting that into action. On the left, well, there's two big markets where we're seeing adoption of RISC-V. Cloud compute and AI acceleration, obviously. On the left, you see a solution where you see our Veyron V2 compute chiplet, and you're tiling it around an I/O hub. This is for cloud compute scale-out type solutions. On the right, you see something built off of our Veyron E2, where you're taking the Veyron E2 soft chiplet IP and creating a customized AI accelerator. So this is not just a roadmap, this is real. It's moved from vision to execution. Our customers are bringing this to market. This is the moment we've been working towards today. When we announced the Veyron V2, it set a new standard for RISC-V performance. We're taking it out in 4 nanometer, and it will achieve 7-second performance, 7-second 2017 performance per core. But we're not done yet. We'll also be following that up with a version in 3 nanometer, which will achieve 8.4 second 2017 per core. There's one thing I want to say clearly now, but it needs to be said. So a lot of times people start talking about spec-in, and they'll say, hey, we're talking to have X amount of spec-in per gigahertz. But that's actually not a real performance target. That's kind of a mathematical gymnastics thing. You have to pick a final target and achieve the F max. So we're hitting the F max needed to hit these these numbers in final systems. The other thing to point out is oftentimes you'll see performance numbers being quoted in, say, Spec 2006. That might be suitable for some workloads, but if you're truly targeting data center today, performance measurements begins with Spec in 2017, and workloads only get bigger from there. But we're not done yet. So today we're announcing the Veyron V3, which will be a follow-on to the V2. So V2 systems are, silicon is around the corner. You can go out there. We have a demo today of our platform running full data center software stacks running on our Veyron V2 on FPGA. But we're announcing the Veyron V3 now, which will achieve over 11 spec in 2017. This is built off of our proven Veyron V2 baseline. It introduces improved IPC, AI and ML features, and improved power efficiency. So with that, I'm going to hand it over to Greg, and he's going to walk into some of the details of what enables us with Veyron V3.
Okay, thanks, Travis. Let's see. Okay, next few slides, I'm going to give you a little bit of an overview of what all is going into V3 and what is fueling this big increase in performance, both IPC as well as frequency. The first thing to note is that our focus is very much on scale-out data center computing. What that then implies is achieving high single-thread performance, but also doing it with very high power efficiency, because at the end of the day, it's all about how much performance can you deliver in a socket within a power envelope. As Travis already mentioned, just single-thread performance, 11 plus a second. From an AI ML perspective, we are configurable and can scale up to delivering per core 24 teraflops of AI ML 8-bit floating point performance. And if you think in terms of a 192-core packaged part, single socket, you're looking at several petaflops of AI performance. We also don't just develop and deliver a core to our customers, but a complete compute cluster of up to 32 cores, a 3-level cache hierarchy, and a high bandwidth, low latency coherent interconnect that enables the performance of that cluster to scale very efficiently from 1 core up to 32 cores, and even past 32 cores. The other thing of note in what we've done is this very much builds on the foundation we established in V2. The large IPC gains we're making as we go from V2 to V3 is through a combination of your traditional types of enhancements to the microarchitecture, as well as a number of new innovations that I'll describe in the next couple of slides. And a key point is that we've kind of laid the foundation for that in V2. In a sense, the foundation, the first floor of a building, and in V3, we then build 3 more floors on top of that to really make this big step forward in IPC performance. Part of what enables us to get this performance and with high power efficiency is we do a lot of maybe atypical and more innovative things. Some of which I'll talk about in the next slide or two is that unlike most designs have an internal instruction set of MacroOps, we actually have internally dense, rich MacroOps, where one MacroOp represents 1, 2, 3, 4, up to 5 RISC-V instructions in compute. And so in hardware, we're able to map RISC-V instructions into our internal MacroOps, to optimize those and to cache sequences of MacroOps. And we do this all software transparently. In conjunction with also identifying, the warm and hot pieces of code, whereas just for that, original, quote, cold code, it's our classic, we can decode many RISC-V instructions at a time, et cetera. But then we get this much bigger boost on performance on all the warm and hot code. Part of what also gets us our high power efficiency is a number of atypical choices we make in our microarchitecture. And this has been true since V1. One simple example is our first level data cache, or DL1, is a fully virtual cache, which eliminates, for example, the need for a complex, power-hungry, many-ported, and typically timing-critical CAM-based L1 TLB. And that's just one small example of many throughout the microarchitecture. And things like this is all transparent to software. It doesn't require any special software optimization or anything. The last thing, which was also mentioned in what we're doing in taking V2 to 3 nanometer, is that we're pushing a frequency through a combination of benefit from the process node, but also doing semi-custom place and route for the physical design, as well as doing targeted, very selective custom high-speed standard cell and macro designs. Okay, a little bit more of just an overview of the microarchitecture that, as you would imagine, is an aggressive, out-of-order design. Superscalar, front-end, decoupled predict fetch, large caches, branch target buffer, load and store queue, schedulers, rudder buffer, you name it. Again, what you would expect for a very high-performance design. There's also a lot of sophisticated predictors, starting with conditional and indirect branch predictors and multiple of them. We also do significant amounts of memory dependence and bypass predictors, load value prediction, and the list goes on. Throughout the entire machine, there's also a high level of parallelism. When you look at the back end, there's lots of execution schedulers and pipelines, as you can see listed here. For all your integer, register, and branch operations, we can do 5 per cycle, along with any mix of 3 loads and stores per cycle, 3 scalar floating point operations per cycle, and 5 vector and matrix operations per cycle, which includes load, store, and 3 arithmetics. And overall, a very large scheduling window in which to keep all that fed with MacroOps to execute. And the next slide, I'll talk even more about MacroOps, but just to make a high-level point, that MacroOps is a much richer, denser internal instruction set, which one MacroOp represents multiple RISC-V instructions. And the entire microarchitecture operates in terms of MacroOps. So you get this sort of a magnification factor in terms of the effective decode width of the machine, the effective size of various queues and tracking structures, the size of the scheduler, even just the number of execution pipelines is effectively all multiplied from, we pay the physical cost, area and power for a certain amount, but we actually get the performance of as if we had a much larger amount of all those various kinds of structures, pipelines, et cetera. And this really avoids this kind of costly sort of brute force approach of going wider and wider in the machine to get more IPC. Again, we do it in a lot more, maybe a smarter, more innovative, very efficient way. Okay, a little bit more about some of this newer area of the microarchitecture that we started in V2 and then we're very much building on in V3. Again, MacroOps can represent 1 to 5 RISC-V instructions. An example is like a load MacroOp can do a complex address calculation in conjunction with the load itself, and it's still a classic 4-cycle load to use. It's not like you're paying more latency or whatever. Similarly with like register and branch operations, unlike the typical RISC-V instructions, that one of our register MacroOps can handle a complex 3-operand operation along with more input and output conditioning, and part of what you're accomplishing is sort of reducing the effective power per RISC-V instruction, since one MacroOp is doing the work of several RISC-V instructions. Now, how do we map from RISC-V instructions to MacroOps. That's where we do this in a couple of stages, but at the heart of it is what we call our advanced fusion engine, which we first identify the warm and hot pieces of code. We'll decode RISC-V instructions into more simple forms of MacroOps, feed that into our advanced fusion engine when it's appropriate on, again, the more warm and hot pieces of code. That engine in the background, purely in hardware, transparent to software, then fuses multiple RISC-V instructions into MacroOps. It also performs a variety of other code optimizations on that code that serves to increase the ILP compared to what you originally had in the RISC-V code, as well as to shorten the critical path through executing that code, all feeding into, again, higher performance. And then we cache the results of that, these optimized MacroOps sequences. And then most of the time we're hitting in that MacroOps cache, bypassing fetch and decode and all the power burned there. And again, I want to emphasize that this is all software transparent. Just as like with virtual caches, some of the reason why people don't try to do those kind of things is there's a number of challenges, which we have addressed all of them, various patents for how we've accomplished those things. That very much applies with our MacroOps cache as well. Okay, last slide. As I mentioned before, we do not just cores, but compute clusters. This is an example of our compute cluster, both with V2 and with V3. 32 cores. There's private L1 and L2 cache hierarchy inside each core, and then a cluster-level shared L3 cache that's sliced so that your L3 bandwidth capacity scales with core count. And again, there's a 2D mesh coherent interconnect fabric that ties all that together in a very high bandwidth, low latency manner. And you can see from the kind of the conceptual floor plan diagram on the right, where the green interconnect slices obviously are larger than what they would be in reality. They're a little out of proportion in size, but you can see how there's both the physical topology is very scalable from 32 cores all the way down to 4 cores. It can even scale up past 32 cores. And then also you can see how the interconnect bandwidth and the L3 bandwidth scales with core count. And also then along the right-hand edge is the interfaces to the rest of the SoC, whether through a die-to-die or whether it's integrated within an SoC, so that even that bandwidth to the rest of the SoC scales as well. And Travis, where are you? Oh, there you are. Oh. I'll let you finish up.
All right. So we've talked a lot about Veyron and high-performance markets. So Greg walked us through the architecture in depth behind the V3. But what's equally important is where that architecture goes. So we've talked a lot about data center, but we also go into automotive, where we have a focus on features such as ASIL BED safety, ECC protection, so we can address that market also. We're also power efficient, so we can scale to other markets such as intelligent edge and the client. Our power efficiency allows us to scale across all these high-performance markets. So let's step back. Ventana is delivering the highest performance RISC-V CPUs with production silicon right around the corner. We're not just promising performance, we're delivering full systems: compute, acceleration, software, and platform infrastructure. AI is baked into our roadmap from the data center to the edge with RISC-V compatible implementations. We're enabling real momentum across the ecosystem, and customers are taping out. Customer partners are building on our platform, and Veyron V3 continues that technology leadership. If you want proof, come by our booth. We'll have a demo today where we'll show full data center platform stacks running on our FPGA. Come by and see us in the lobby. Thank you for your time.